Welcome back to all my returning students and a big welcome to our class for all you new people. We're going to have a little lesson on how to science. This is an intro that'll give you some information on how to navigate class as well as how to do science in general. There is a whole lot more detailed information on how to navigate class that will be presented at the Grill and Chill event. If you're unable to attend that, please be sure you check out the slides that are available to you in your resource folder in Dropbox. That'll help you navigate everything this year. All right, so first things first, you're going to need to have your class binder and a pencil handy. Now, if you do not yet have your binder, you will need to access your student Dropbox. And again, if you aren't sure how to do that, that will be discussed in the Grill and Chill. Plus, you can also go to our website, go to all the links, enter this year's password, and it will take you where you need to go. You're going to need access to your preface section of your binder, the syllabus section of your binder, as well as lesson 1. If you haven't already done so, you need to read or skim through the preface and the syllabus section of your binder. You'll notice that your binder's pages are subdivided by section and are numbered accordingly within each section. So let's talk for just a minute about how we do grading. So we have a specific weighting pattern for our assignments listed here, and this is also going to be located in the preface section of your binder. We're going to discuss assignments a little bit here, so we need to keep this grading scale in mind for context. So once you have read and skimmed through the syllabus and the preface, turn to the first page of lesson 1. So flip through the pages of lesson 1 and notice any blank spaces. You will often have blank spaces to fill in as part of your weekly assignment. You'll fill in the blanks as you work through each week's lesson while reading or while watching a video, like this one, for example. And these pages will remain in your binder to help you study and prepare for tests. Now here is where I'm going to go off topic for a second, and this is how you're going to get credit for this particular assignment. Every so often, I'm going to stop and drop a hint about my favorite movie. And at the end, you will get to go into your gradebook and teacher ease and enter what you think the answer is for credit. Now I'm going to continue. You will usually have a homework assignment to follow for each week's lesson, and on the final page of each lesson, right before each week's lab, you'll find your homework page. This page will show you whether your homework is to be completed through your online portal Teacher Ease, which is usually the case, or if it's to be completed on paper and uploaded to your portal or physically handed in. This same exact information is provided on your syllabus and in Teacher Ease. There may be some changes to the syllabus throughout the year, but I'll let you know if that happens. In science, we call this kind of repetition of information redundancy. If you haven't already logged into Teacher Ease, you'll want to pause and do that now. You should have received an invitation to your Teacher Ease portal. So one category of assignments on which you'll be graded is your homework and binder work. This category of assignments is worth 15% of your grade. So I want to discuss this one with you because sometimes it can be a little confusing the way this works. So to receive credit for your binder work, I have to have a reason to believe you've completed it. If you are participating in the class discussion, answering questions, sitting with your binder open, I have reason to believe that you're keeping up with your binder work. At any point though, I can walk around class, stroll around, look over your shoulder, or check on your work. Most binder work homework, oh, brownie point, I caught it myself. That should say homework binder work, not homework. Assignments will begin with an unrelated, often silly question. There's no way to get it wrong, okay? What happens is when I see that you've answered that question, it triggers me to think about whether or not I have reason to believe you've completed your binder work and then credit you for that work. There's an example of a silly question over here in the screen capture of an assignment, and it's the first question, and it says, what is your most used emoji? So to receive credit for your homework, you have to turn it in as instructed for each assignment and turn it in on time. So your homework and binder work together is worth about 15% of your grade, and it works out to your homework being about 10 of that 15% and your binder work being about 5. The points for each homework binder work assignment will be counted on the day the homework is due. So we may have class on one Tuesday, and then I have to think back to decide whether or not you're going to get binder credit for that Tuesday, but it's usually about 5 or 6 days later when I'm making that grade, putting in that grade. That's why it's important for you to answer the binder work question, because it triggers me to think about you specifically and whether or not you seem to have been participating. So my favorite movie is what you would call like an ensemble cast. There's not really a star. I mean, some of them today are really big stars, but back in the 80s when this movie was put out, 1985, I'm pretty sure, most of them were kind of unknown, although at least one of them is the son of somebody who is a very famous actress and a very famous actor. And then another one is actually these days, I think somehow related to Barbara Streisand, maybe through marriage. On the back of your weekly homework assignment page, you will find an image of Rico. This is our mascot, this little dude here. You'll see him everywhere. If you're new, you haven't seen him before, now you know who he is. So each week you're going to have an opportunity to color him according to a theme and turn him in for a prize. The prize is usually a little piece of candy. So keep on flipping, and at the very end of each lesson section of your homework page, you will find your weekly lab. So sometimes you're going to turn in your lab the following week, and sometimes you're going to complete it in class. Sometimes you're going to turn in an individual lab that you've completed by yourself, and other times your team is going to turn in one assignment as a group. You will be working with a team in lab. We have 4 lab teams, and they will change members every quarter. So now you're going to flip back to your first page of lesson 1, and you're going to notice here that your syllabus entry, which is at the front of your binder, behind your preface, is exactly the same as what is on the first page of your lesson. So here are 2 places where you can find your assignments for each week. And then, of course, they're also in your grade book. And this is at the end of every email I send every week, too. So to know where they are, you can look in either of these places or the other 2 I mentioned as well. So again, like I said, we will discuss how to navigate class with much more detail at the Grill and Chill. So if you can attend, be sure to review the slides that are available in your student Dropbox, as well as the Grill and Chill assignment in Teacher Ease. So now that you know what to do for class, let's get started with some basic info on science in general. Rico presents How to Science. All right, so what is science? Google defines science like this: the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. That's a mouthful, so let's break it down. Intellectual, let's say mental. Practical, hands-on. Encompassing, let's say surrounding. Systematic, organized. Structure, construction is another way to say that. Behavior, we'll say actions. Physical, we'll say touchable. Natural, we'll say real. Observation, we'll say watching, although it can also be smelling, sensing. Observations are not necessarily visual. It's anything that happens with your 5 senses, or 6 if you want to include proprioception. And then experimental, or experiment, let's say testing. So let's rephrase it. The mental and hands-on activities surrounding the organized study of construction and actions of the touchable and real world through watching and testing. Or more simply, the study of the natural world through knowledge about the natural world that is based on facts learned through observation and experiment. So science is broken down into 3 main branches. You have your formal sciences, which are things like mathematics, logic, and statistics. You have your social sciences, which are things like societies and human behavior. And then you have your natural sciences, which break down mainly into physical science and life science. And life science is things like biology, zoology, ecology, genetics. Physical science includes things such as physics, astronomy, chemistry, and earth science. Physics itself is a more advanced class than physical science. Physics involves a lot of math, high-level math. So this year we are doing physical science, which is sort of an overview of things like earth science, a little touch of astronomy, a little touch of chemistry, and basic physics. So what are the big ideas in physical science? Well, they're things like space and time, matter and change, forces in motion, and energy. So for space and time there, I give you not really an astronaut, I'm sure that's some sci-fi thing. I don't know, it was a good picture. And an hourglass. For matter and change, for matter I gave you some sort of an atom, and then change. I wanted to point this out to you. That triangle is a delta. That is the sign for change. You're going to see that a lot this year. Forces in motion, I gave you there some military forces to keep you thinking along the lines of forces, and the arrow for motion, and then in energy, of course, we did some batteries there. So scientific theory versus scientific law. Anybody who's ever taken a class with me knows that this is something I feel that is extremely important for you not only to understand, but to understand it so well that you can recite it. And it goes like this. Scientific theories versus scientific laws. First, real quick, did you see little Rico spin up in the corner there? It says engrave it for eternity. I try to remember to stick that into any lesson where there's a particular topic on a slide that I think you need to remember forever and ever. It's a big time learn it, not just like learn it as part of this lesson, learn it forever. So in studying science, what's the difference between a theory and a law? I said scientific law tells what happens, a fact. A scientific theory tells why it happens, an explanation. So a fact about my favorite movie is that it takes place in the city of Astoria. So this is important. In this class, we're going to study scientific law and scientific theory. For example, there are multiple theories of origin. This class is a science class, and it's going to be taught from a scientific perspective. Any theories of origin discussed in this class will be scientific theories. Different people hold different personal and religious beliefs, and it's safe to assume that all questions and answers in this class are prefaced with an unvoiced according to scientific theory rather than I personally believe that. Okay, so this is important to remember because it's science class. We're looking at things from a scientific perspective, and all of our answers are coming from a scientific perspective. Your personal or religious beliefs about any topic we're covering, you're free to hold them. Obviously, they're yours. They're personal, but they don't necessarily play into the lessons we have. Why is measurement important? You know, in my favorite movie, there is a map that the characters use, and a lot of the measurement is given in paces. And that is kind of a nebulous way to do it because it's not very, what's the word I want? Specific. Your pace and my pace might not be the same, but still they managed to get by using things like paces. All right, so measurement is important. If you stop and think about it for a bit, you'll realize measurement surrounds you on all sides, and measurements matter. So some things that we measure are length, mass, which is how much matter, weight. Now there's a difference between mass and weight. If you put me in space, my mass will not change, my weight will. Weight is the effect of gravity and mass together. So the effect of gravity on your mass determines your weight, but your mass is how much matter there is, or how much of you there is, or how much of any particular thing there is. Area, which is two-dimensional. Volume, which is three-dimensional. Density, which is how much mass is in a contained space. Time and temperature. In the US, we commonly use the imperial standard or customary system. This is what you're used to, inches, yards, cups, pints, tablespoons, miles. But in science and most other countries, the metric system is most often used. The metric system may seem unfamiliar at first, but it's actually much easier to work with once you understand it. The metric system is base 10, so once you learn the units and the prefixes that kind of tell you how many of those units you're dealing with, it is so much easier because you don't have to do conversions from inches to yards or tablespoons to pints. So this is what metric conversion looks like, and we will be going over this in class and using it fairly frequently this year since we are doing physical science, which does involve things like forces and motion, and it will involve things like mass and weight. So you have a unit that's right there in the center. Meter is the unit for length, liter for volume, gram is for mass or weight, and then there are the abbreviations for those are right below them. And then you have prefixes that you put ahead of the units that tell you exactly how many of those units you're using. So if you look to the right and to the left, you'll see that all the way to the left, for example, 1 kilo is 1,000 units. So a kilometer, is 1,000 meters. A hectometer, or that people don't usually say hectometer, but hectometer anyway, that would be 100 meters. Or for example, a decaliter is 10 liters. Now, if we're going to the right from there, they're getting smaller in this case. So a deciliter would be 1/10 of a liter. And a centigram would be 1/10 of a gram. Now, I mean 1/100th of a gram, I'm sorry. And you've probably heard it centimeter before, and that's 1/100th of a meter. So if you take a meter stick, you're going to find 100 centimeters on it. And then you have milli, which is the unit for a thousandth of one of your units. So you'll have like a milligram, which is a thousandth of a gram. So you're dividing by 10 in one direction, multiplying by 10 at the other, which is at the bottom, and we'll practice this. And if you need to remember them, a lot of people do. King Henry died unusually drinking chocolate milk. You may have heard King Henry died Monday drinking chocolate milk. Monday was meter, but it's not always meter. Sometimes it's liter or gram. So King Henry died unusually drinking chocolate milk. There was no chocolate milk in the movie that is my very, very favorite. There was, however, ice cream from Swenson's in a freezer that one of the characters found and was super duper excited about because they had Rocky Road. I know that's one of them, was Rocky Road. So how do you present data like a scientist? Okay, so scientific notation. We will be using this year, and definitely this gets used in chemistry. So scientific notation, real quick, I'll just point out at the bottom there. Sometimes numbers get really, really big or really, really small. So we tend to turn that number into a decimal and take the number of zeros behind it and give it either a negative exponent or positive exponent. And that might not make sense right now out of context, but when we get to it, it'll be better explained and you'll remember that you've seen it before. So data are the information gained from observing and testing an experiment. Data is actually a plural word. Datum is singular. And the funny thing is, in my favorite movie, there's a character named Data. Scientists use data, not the character, to gain understanding and make conclusions. So what's a hypothesis? A hypothesis is an idea that can be tested. The characters in my favorite movie definitely hypothesized that if they followed the steps presented to them on the map, they were going to find a treasure. So here are the requirements for a testable hypothesis. Remember, it's an idea that can be tested. So not every idea is a hypothesis. Like you can have an idea that you want to, paint your house purple. That's not testable, really. I mean, you can do it, but it's not testable. So here's what it means to be testable. In order to be considered testable, it must be possible to prove that the hypothesis is supported. You can think of it as true, but really the word is supported. Or it must be possible to prove that the hypothesis is rejected or not true. Rejected and supported are the ways to phrase this best. And it must be possible to reproduce the results of the hypothesis. So there's your little engrave it for eternity. Don't ever forget this one. All right, so many scientific hypotheses, which is your plural, are proposed in an if-then format because it's easy to design an experiment to see whether or not a cause and effect relationship exists between the independent, sometimes you'll hear it referred to as manipulated variable, and the dependent or responding variable. And we'll talk about variables in a minute. So what if a hypothesis is supported? So a scientist will make sure that she can repeat her process and replicate her results. Because remember, in order for a hypothesis to be testable, it must be repeatable. So what if your hypothesis is rejected? A scientist will revise his hypothesis and often repeat the experiment. So scientific method. Scientific method. So this is how you test your hypothesis. So you have to use this in order, if you're going to think like a scientist, you're going to test your scientific hypothesis, using a scientific method, and conduct a controlled experiment. Now, you can't really think of this. So you can't really think of the scientific method as a linear process, like step A, then step B, then step C, because there are definitely some ways you can make turns along the way, depending upon what sort of results you are getting from your experiment. And we'll be using a lot of scientific method in labs this year, so you'll get to practice it quite a bit. So here are variables. Now, I said we would talk a little bit more about variables, so here we go. Your independent variable you can think of as what you change. Your dependent variable is what you observe. And your controlled variable is what you keep the same. So in a controlled experiment is one in which only one variable, the independent variable, is deliberately changed at a time. So I want you to think about an example where, let's see, you have frequent headaches. And you're trying to figure out if there's a particular thing that causes your headaches, or how about this? No, you're trying to think of a way to get rid of your headaches. What's the best method for getting rid of headaches? So you come up with a hypothesis that resting in a dark room is the best way to get rid of your headaches. So you take yourself into a dark room and you take some Tylenol and you take a cold compress for your head and you lay there in the dark and your headache goes away. Okay. You just added multiple things to your experiment. How do you know if it was the Tylenol or the cold compress or the dark room? You don't know. The only way to determine whether or not it's the dark room is to change only that about your behavior. Go and rest in a dark room only, don't take any medicine, don't put on the cold compress, and then see if things change. So how do we be a good scientist? Well, I know for that one character in my favorite movie, that guy Data, he really wants to be a scientist. He actually has tons and tons of inventions. And it's cool because some of his inventions are used throughout the journey where all these characters make their way to the treasure following this treasure map. And they do some crazy stuff, for sure, some crazy stuff. All of them, like Mikey and Mouth and Data and Chunk and Brand and Andy and Steph. Yeah. So how do we be a good scientist? Well, we're going to engage in arguments using evidence, not emotion, people, evidence, okay? You're going to ask questions, define problems, develop and use models. Models are great. We'll talk about models more this year. Models are a great way to exemplify a topic or a point or a concept that is maybe a little abstract. Like think about solar system models. That's a great way to visualize something that you can't visualize on your own. You got to plan and carry out your investigations, analyze and interpret data. Always analyze and interpret your data. Try and figure out what your data means. You're going to use math and computational thinking, construct explanations, design solutions, obtain, evaluate, and communicate information. And that's part of using models. This is how we be a good scientist. So one way to open your eyes is to ask yourself, what if I had never seen this before? What if I knew I would never see it again? And this is a scientist named Rachel Carson. And her work increased the understanding of environmental dangers of a certain chemical called DDT that used to be used to help get rid of mosquitoes. Mosquitoes carry diseases, so you definitely want to get rid of them in certain situations. But it turned out that this particular very popular chemical was causing damage as well. And thank goodness for Rachel Carson figuring that out. Life is not found in atoms or molecules or genes as such, but in organization, not in symbiosis, but in synthesis. And this is Edwin Grant Conklin, and he pioneered the fields of cellular lineage and embryology. Cellular lineage is like, so you've got maybe an embryo developing and there's only 4 cells. Well, one of those cells is going to become particular body systems. Like one might become the nervous system and a different one might become the digestive system. That's cellular lineage. It's pretty cool, actually. It is not the strongest of the species that survives, nor the most intelligent that survives. It is the one that is most adaptable to change, and this is Darwin. Darwin developed theory of natural selection, and his hobby was breeding fancy pigeons. If you want to see some weird stuff, start Googling Darwin's pigeons. He's less known for the pigeons, but it's one of my favorite facts about him. A lot of people like to say survival of the fittest to sum up the concept of natural selection, but that really does not sum it up properly. Properly, the thing to say is that it's the most adaptable to change that is the one that survives and passes on its genes to the next generation. And then we have, I am among those who think that science has great beauty. A scientist in his laboratory is not only a technician, he's also a child placed before the natural phenomena which impress him like a fairy tale, and that's Marie Curie. So she is known for her discovery and work with radioactive elements, which aided in cancer treatments. She has a fascinating life story as well, and definitely one of my favorites. So settled science. This is another big point. Lastly, never forget, no matter who says otherwise, science is never settled. Okay, why? Because let me tell you, you're going to hear the science is settled a lot. We hear it when it comes to climate change. We heard it a lot with the COVID pandemic. Science is never settled. Why is this wrong-headed? Okay, I'm going to tell you why. And this year, I'm going to do you the favor of summarizing each of our 3 big points into one little, like a little sound bite or a little chunk that you can keep in your head and maybe memorize a little more easily. So there's our little engrave it for eternity, guys. So this is one of my points to keep forever. So this concept that science is settled is wrong because 1, it presumes science exists in a binary state, that science isn't settled until it crosses some imaginary line after which it's finally settled. On the contrary, science by its very nature is never 100% settled. Science does not exist in a binary state. That's the way to sum up number 1. It's not like it's on or off, right or wrong, black or white. Number 2, another reason. It presumes that poor understanding in one area of science invalidates good understanding in others, and this is not the case. So this one's the wordier one. But it's poor or good understanding in one area of science does not validate or invalidate good or poor understanding in another area. Basically, there are some things we know a lot about, and there are some things we do not know a lot about. And lastly, the third point. And this is one some of y'all tend to miss this one. So natural science is not about absolute proofs. It never reaches 100% certainty. This is the domain of the formal sciences, which, as you remember from our slide before, was like things like math and logic. Science is about improving our understanding by narrowing uncertainty. Different areas of science are always likely to be understood with varying degrees of confidence, which goes back to point number 2. So the goal of the natural sciences is to narrow uncertainty. Well, as the characters in my favorite movie made it from, the fireplace underneath the old restaurant, and the Fratellis were right behind them, it became less and less certain that they were going to make it to their goal safely, but somehow they did. And they got to see One-Eyed Willie's treasure. So you can just ask these guys because they prove that science wasn't settled. Well, you can't really ask them because they're all dead, but there's Galileo Galilei who proved the sun was the center of our solar system, not the Earth. That's a huge deal because for years and years, the consensus was that the Earth revolved around the sun, and he proved it wrong. Darwin, again, introduced the theory of natural selection, providing the first explanation for the idea of evolution. Evolution, the thought that things change over time, that species change over time, had been around for a long, long time. But it wasn't until Darwin posited the concept that it's the most adaptable that survive change in the environment and are able to pass on their genes. That concept of natural selection is what provided an explanation for evolution. Lister applied germ theory to create the concept of sterile surgery. If Lister sounds familiar to you, maybe because you've heard of Listerine, which is named for Joseph Lister, and Listerine is obviously antiseptic, kills germs. Prior to Joseph Lister understanding and applying germ theory to things like medicine and surgery, we're talking like, you use a bone saw on one guy out in the field after his leg's been shot with a musket, and you slice it up, and then you take the same bone saw to the next guy, and then you just leave it in the mud until you're ready to use it again. We can't even think about that these days. I mean, we can't conceptualize that because to us it seems crazy, but prior to him, people really did not think diseases were passed on that way. Wegener. Okay, if you did Earth Science with me last year, you know Alfred Wegener. Alfred Wegener originated the theory of continental drift. He was able to explain why continents move over, well, not why. He was able to explain that continents move over time. That we used to have Pangaea, which was this big, massive continent, and that continents shifted around and things weren't always in place. And he gave evidence for why this happened. But his theory was not well accepted at the time because he did not provide a mechanism for the theory, which later we learned was plate tectonics, and it has to do with convection heat in the mantle of the Earth moving around our continents. But he wasn't able to provide data for that, so people kind of laughed at him and thought, continents moving, that's silly, that's ridiculous. It's kind of like Darwin came in and he provided the mechanism for evolution, whereas Wegener just said, well, this happens, and he was right, it did happen. And then how about Robert Goddard? He was laughed at for suggesting that we could travel to space using a rocket. And that's kind of funny because now it seems like every day some billionaire is going somewhere in a rocket, or, you know, we do it all the time. We've been doing it since the late 1960s. And here's our guy, Robert Goddard, who suggested it and got laughed at. So who will make the next great discovery? Well, I think, you know, when my characters in my favorite movie finally discovered One-Eyed Willie's ship, the Inferno, that was probably the greatest discovery of their lifetimes. So who's going to make the next great discovery? You never know. It could be you.